Hi, my name is Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. So I hope we'll have a clean stream tonight. I think that the shared internet is not being shared as much as it was the last time we tried this. And so hopefully you won't get any unwelcome adverts in the course of this presentation. So I'm extremely excited to share with you today what I have for you. But before I get going, can anyone confirm that you can hear me? And okay, so great common misconceptions. Okay, hi Mighty Mouse girlfriend. Hi Simeon. Hi Gordon. Hi Corky. Hi, who we got in the house? FPV, Angel, P900 Coolpix. Artifact, Stuart, excellent. Oh, and Simeon, I'm glad you've been able to read Space Earth Human. Yes, I recommend it to anyone that is interested in understanding the fundamentals behind this science, and also some rather quirky things as well that led Alexander Parkhomov to be in the right mind space to be able to discover the N radiation, which later turned out to be relic neutrino flux from the cosmos. And that helped me in my understanding when you guys clubbed together to make it possible to make that translation so that the world can read it in English. Okay, so hi from Sweden, Maria, and hi Michael. It's great to have you here. Okay, so I had intended to be very specific about what I am sharing tonight. However, when I went to bed on Friday night, which was quite late, after the last presentation, I had something on my mind, and essentially I couldn't really get a lot of sleep, and I was kind of running through oxidation states of various elements and what the possibility was, and also I was uncomfortable with having to wait all the way to October to be able to confirm whether we were observing this FeO2, which is a high oxidation state of iron, which is higher than Fe2O3 magnetite, I think that's right, that hitherto until 2016 was supposedly the highest oxidation state of iron, and ever since the FeO2 phase has been both proposed and then produced in diamond anvils using 76 plus gigapascals of pressure and 1800 degrees Kelvin, that is over 750,000 atmospheres. It's been a bit of a hot topic in the condensed matter physics world, and I've been sent various papers that are, you know, right hot. And the other interesting thing was that I was sent by a follower of the project some work by a Japanese researcher who was claiming that by using dopants he could get to higher oxidation states than Fe2O3, and he was able to use this material. As I understand it, I haven't gone into the patents in any great depth, but the claim is that when you have this very high oxidation state, it will actually dissociate water or produce hydrogen, I think the phrase was, so at room temperature or something like that. Like I say, I haven't gone into it, but that is very interesting. And the FeO2 is actually at a higher state. Now, if it is true that this is FeO2 in these, what I believe are the magnetic core of ball lightning and these monopole type structures, and I'll go into why using a number of slides from presentations going back to 2018, probably if I get to it, why I have thought for a very long time that this is, it was inevitable that the core, the magnetic core, would be a sphere and that it would be iron rich. And so you hopefully by the end of this presentation you will understand why it was a very easy educated guess that the reason things were getting magnetic in the ultra experiments was that these structures were being formed, and that it was almost certain that if one actually bothered to look, they would see a crenellated iron-rich oxide sphere produced in these, and that is exactly what was found by one Alan Goldwater after about 10 minutes of work prior to drying and putting under the SEM. But it was a very satisfying process. Anyway, I have been speaking off and on with Bin-Juine Huang, who is the professor at the New Energy Center, Department of Mechanical Engineering, National Taiwan University, Taipei, Taiwan. And at ICCF22, he gave a presentation where he was putting water through pipes and copper pipes, and this was creating excess heat. And the assumption is that it was cavitation, and he was finding this sort of blackened, kind of smooth surface on the inside of these pipes. And I asked him whether he had analysed it on the SEM, and at the time he hadn't, and then he did, and it came out as expected, as copper and oxygen, and copper and carbon. And then he has conducted some experiments which he shared with me the data, and we're going to have a quick look at that. But before, I am going to show you something which, like I say, wasn't going to be scheduled for today, but like I say, when I see something, I want to get it out of the door as conceivably fast as possible. So this is the title for today, Ultra Crop Circles. And why I'm calling them that, you'll need to see to the end. But I will be asking for some assistance, and I think there are people out there that are better placed than I to assist this part of the investigation. And I think that we might learn all kinds of things by cross-correlating. Anyway, this is the title of the presentation. And on the left, you can see, if I change my mouse controller, you can see here, this is some copper foil that was put into an ultrasonic device by Professor Huang. And this is the SEM that he took. And on the right, this is the SEM that I took on Monday of this week, and we are going to have a whole series of SEMs that we are going to look at, and it's really rather exciting what you are seeing in these SEMs. But before we do that, I am going to show you this. Right, so as you are probably aware, if you were watching the previous presentations, and I will get rid of my mugshot, this is the magnetic core O2 that was found in the Vega Valley on Monday of this week. And I'm going to put my face over that so you can see what I'm blathering on about. And so it was found that the ratio of the oxygen to iron was 2 to 1. In fact, it's 2.05 to 1. And I was thinking there are some other elements, and if you actually look at this area, there are some bits that are caught into the sample area here, which are obviously not part of the main structure, or they are features on it. Now, I've since looked at this structure and the other structure, and I don't think these are in necessarily random places, but it's, for instance, there's a little lump up here, and it's caught the edge of that. So I think that the zinc and copper that you are seeing here, and possibly the sulfur on this sample point 39, are actually these bits that are on top of it, not the actual material. That being said, the oxidation states of the other elements, if we take carbon, which we've got 2.88% in the atomic ratio, is O2. O2 is O2. Sulfur here is sulfur dioxide. So these are the kind of like the maximum oxidation states, as far as I understand it. And those with the better chemistry understanding might like to step in and say, no, we can get zinc peroxide or copper peroxide. Well, you kind of can, but it's kind of got a hydrogen in there or something. So this is cuprous oxide. Cupric oxide is Cu2O. So that would be a 2 to 1 rather than a 1 to 1 ratio. Now, given that these are all at best 1 to 2 ratio, and in the case of CuO, which is 1.57%, and ZNO, zinc oxide, is 1.87%, and that those are 2 to 1 ratios. The fact that we have a 2.05 to 1 ratio for the oxygen it really does point, and all I'm doing is taking that to that. I really should add all of these bits up and that, and maybe do the oxygen as well. But I think, given the fact that we are looking at this bit being caught in here, this bit being caught in here of other material, I think that we could well be in a position where the iron and oxygen is that 2-to-1 ratio. And what I would do to confirm that, and I can see probably I should have added all those up, so nothing's perfect. What I will do when I look at this again and look at the other one that's over here on the left of it, this one that's exactly the same size, is I will do spot samples on clean areas of this. And I think that probably we will therefore see pretty much exclusively iron and oxygen with some trace element on there, and I believe that we are going to hit that 2-to-1 ratio. And if that's the case, then this is probably the largest sample, because it's what is it? I think we worked out it was 27 microns across. This is the largest sample of FeO2 in the world, in a lab anywhere, on its own. And there's another one the same size over to the left, because I think the samples that they make in these diamond damples are really, really small. They're really small. They've got like a laser going through them to work out the phase change and stuff. But anyway, so there we go. Now, so I was thinking, you know, oh, hold on a minute. This isn't the only one that I did, was it? We have our magnetic core 1, and if you recall, this was on the earlier analysis that I did in August. And then this is the image that was taken on the beginning of this week. And this was literally the first thing I went to look at, because we wanted to find out what this was. And if you remember, it's kind of like sucking the light out of the room. When I say light, the light in this case is electrons coming in, hitting the material, and then producing X-rays, and they're coming back. And what you're seeing here is the kind of like secondary electrons here, secondary electrons. You've got electrons coming in, they're hitting and coming away, and you've got this is a secondary electron image. The point is that this seems to be sucking the electrons out of the environment, which is quite interesting. And it's very, very bright. And normally, something that's very bright, you would say, is actually a much heavier element. But as we know, these are all zinc and copper around. So this isn't the heavier element, but it's actually much brighter. So what is going on? It's kind of a bit weird. And you do kind of get this with things that charge. That is to say, if you get something like a silicon dioxide, or you get alumina in there, and particularly silicon dioxide, you see this a lot, and it gets charged, i.e. the electrons are building up on it, then it ends up looking a bit whiter anyway. Just show you, the title of the slide is Magnetic Core 01. There we go. And so, you know, you could say that maybe this is silicon dioxide, and maybe that's a thing. Maybe there is a layer on it. But when we zoomed in, we saw almost like this atmosphere. It's kind of like the equidistant all the way around it. And I speculated at the time, before we went in a little bit further and managed to find some combination of parameters that allowed us to see what's under the atmosphere, like down into the core of the core. I speculated that this might be some sort of electron cloud, because it's basically sucking the electrons out, the secondary electrons out of the environment, and maybe even the primary electrons. Okay, so I thought, is it sucking the electrons out of there? And if it is, then if the iron FeO2 was to be put into an environment where it could grab the electrons from, you know, hot water, maybe it would cause the water to dissociate. You know, I don't know. But anyway, that's just a thing to think about. Anyway, so looking at this, what do we have? Well, this is our globe here, and I'll show you the title, which is Magnetic Core 01. And we have 3 sample spots that we took on here. And if we look at them, And over here, I've got the weight percent. So this is weight percent here on the right. And down here, we have the atomic percent. And you'll see for one, again, there are 3 small spots, maybe 4, which are within this one area, which are not the same material. Particularly this one, and this one. There's a lesser one here. These will be clear when you see the slides. Anyway, so that would imply that there's some sort of contamination from the actual sort of glassy pinecone type substrate underneath. But that being said, the ratio here is 2.18. And silicon is below the level at which you would consider it even there. And copper also is under 1% atomic percent. And so, you know, and in fact, actually, if you look at one over here, silicon and carbon are in red, which means that the certainty of them being there in that sample area is too low for the software to actually categorically say that they are there. So the only elements that the software is saying is actually there is iron, oxygen, zinc, and copper. So iron, oxygen, zinc, and copper. And given that these are so low, and both of these elements are essentially maximum oxidation state of zinc oxide and CO oxide, that's 1-to-1 and 1-to-1, I think it's very, very likely that this is achieving a 2-to-1 ratio, that this is FeO2. And the other thing that I noticed when I was putting this table together is that the sample that I did in the middle, which again has a little bit of contamination over here, okay, this little spot here, but this is this center, which is darker, and I think we established that by playing around with the contrast, this is actually a sphere, but this center is a bit darker, that the actual ratio of this is much lower. Now, we do see that the, actually, no, there's not actually much more copper and zinc in aggregate, and so this is lower. And so could it be that this actually isn't a south pole and therefore it's sucking the electrons in? Could this be that this is either a north pole or that it has insufficient iron and oxygen to form the intense magnetic state, or this special structure of iron and oxygen, that it's playing with the electrons in a different way? I don't know, but there's some things to think about. Okay, so that's that. And then, so does anyone have any comments on that before we move on? Anyone have any comments before we move on? If not, I'll move on. Okay, so we're going to have a quick look at the slides that were sent to me by Bin-Juine Huang, Professor Huang. But before that, I just remind people that he sent me, I did a proposal for the observed oxygen and carbon in his previous data, looking at the pipes that he produced excess heat with his kind of cavitation system. And I won't go into that because it was a very detailed 2.5 hour or 2 hour presentation where I went into a lot of detail. So I won't go into that, but what we can say is that the cavitation is synthesizing carbon and oxygen on copper, and that is well discussed in this previous work. So we'll look at the work that he sent me on August the 3rd, 2021. And cavitation-induced rupture of copper foil by ultrasonic vibrator. So this is a ultra-like experiment. It's not quite an ultra experiment, and you'll see why. But here it is. This one is for 7 minutes, so he's going all out with this, and 21 minutes. So this is like poor copper. That's all I can say. And he says cavitation-induced rupture of copper foil, and the copper foil here was 0.08 of a millimeter, immersed in the water of an 300, you can't see that because I've got that my face over the top, immersed in the water of a 30 watt ultrasonic vibrator for 7 minutes and 21 minutes. So you can see at 7 minutes it's damaged, at 21 minutes it's more damaged. And he is saying that the failure mechanism is both mechanical and thermal. Anyway, here is the money shot from this. And essentially he has a number of pits, okay, and you can see it on the color images as well. And the pits here, if you look at the spectrum, if you look at spectrum 3, which is the bulk of the substrate, that has 9.96% by weight, and the spectrum 2 has 15.49% by weight. Now, the reason I'm highlighting the by the weight in this instance is that if something is by weight and you have a heavy element like copper, which has got 63 or 65 nucleons, and you have carbon, which only has, let's say, 12, then this 15.49% in atomic would be quite a bit larger in terms of the number of atoms than the kind of impression that you get from the change from 9.96 to 15.49. It's a bigger change than it would appear in terms of weight percent when you are referring to it in atomic. So it's actually quite a lot larger, and actually you can actually see that it blackens. And so, like I say, we've described that. And here in the other experiment here, you can see this pit with this other ring around it. I believe this is important, and the pit shape on the outside, which is starting to get this kind of hexagon feel to it. This where you get these diachron type instabilities, where you get something spinning in the center, and then you got things spinning around the outside in some sort of self-organized structure, like the top of some gas planets in our solar system. And you see here that the background here, spectrum 2, again, 8.69% here. Again, it's weight percent. And then if you look at this center here on spectrum 3, it's 14.45, and the darkened area over here, 17.08. Okay. Now the other thing he says, I'm getting silicon now. I'm getting silicon. So where is the silicon coming from? Well, the silicon is coming from, in my view, fusion, and you can go to nanosoft.co.nz, the Philip Power developed Parkhomov reaction table inspired and sort of put together by myself and Philip, reaction calculator that's free to use at nanosoft.co.nz, but the fusion version, so this is 2 to 1. And if you put in element 1 is carbon and element 2 is oxygen, and you order by fitting it into the smallest box, i.e. the most energy is at the top, that is the thing that fits into the smallest box, you have all of the carbon and oxygen isotopes, 16, 17, 18 here, 12, 13, 14 not because it's radioactive, so that's not included in the tables here. Carbon 13, 12, and oxygen 16, 17, 18, they all fuse to the isotopes of silicon. So here we have something where we can get silicon from this reactor, which is essentially just sound and cavitation. Now, the thing about this is what I can see when I'm looking at these damage marks is I can see that I don't believe that Professor Huang was holding the sample in a fixed position. And what this means is that you can't get the resonant node set up and then acting in the same place over and over and over again. So if you imagine, it's kind of like imagine Tesla is looking at that snowball down a mountain. That snowball down a mountain, that is what inspired him to realize that if you keep adding at resonance and not taking away, ultimately you will have a irresistible thing. And it's kind of like having the snowball down the mountain and then moving the mountain away. In the case of Leclerc, what he was doing is he had aluminium, or aluminum for those of you in the States, and he had punched holes in it, and then he was putting pressure water through that would then go through these holes, and I think because of the pressure regime, that would force cavitation. And that means that the cavitation is occurring at the same edge at the same time all the time. So whatever resonance is set up, whatever coherence manifests itself, you're then pumping that coherent structure, pumping that vortex, pumping that vortex, pumping that vortex. And that is why I believe he was able to get every element in the periodic table, rapidly go to uranics and transuranics, and those would decay back to radioactive isotopes, because he is forcing the system. This is similar to the Ultra, but Ultra is much more gentle, and you're not running it for a long period of time. Don't do that. Do short experiments. However, I will kind of suggest at the end of this presentation, what I've suggested to Alan is that we need to kind of do a series of experiments where we are running an experiment for 90 seconds, then we're doing 180 seconds, then 360 seconds, and so on, and then seeing the progression of synthesis that occurs, so that we can get a sweet spot where we are synthesizing something more interesting than iron, and maybe synthesizing things that are more useful but not dangerous. And so now the thing is, I think that probably Bin is not observing iron in here, because he's actually got a heavier element than iron, and so it's kind of really the water that's doing the work here. And there's plenty of oxygen and plenty of hydrogen in that water, and so the transmutation to iron is harder. Why do I say that? Well, because if you take two 27 nanometers and fuse them, that gives you iron 54. So you've already got something that's readily getting to iron without much effort. Where you've got something like copper, you're going to got to work backwards. And really, if the coherent system is going to do anything, it's probably going to work on making carbon and oxygen and these kind of silicons, and that's exactly what you observe here. Okay, so now the feature that I think is interesting here, though, that he captured, and is very clearly captured, is this. And this shows the vortical nature of this, okay? Where it's split the copper in this S shape. And it's not just that. Look what you see in the center. There is actually a circular section in the center. And I think that this is where you would see the core of the vortex making this circular section. Now, I'm not saying he didn't produce iron. I'm saying that if he did, he didn't do the magnetic thing to extract the material from the reactor, because this is not too dissimilar for what we're doing in Vega, except we're using direct electrical field rather than creating it via vortices and cavitation and charge separation with the polar molecule of water. And so in this instance, he may have actually created iron-rich spheres, but he didn't look for them, and he didn't even look to see if the pieces of copper would move. He may have even created fragments that came out of something like this that were heavier elements than copper. But his interest was to look for changes on the copper, because he had seen changes of carbon and oxygen increase on the surface of the copper pipes in his energy generator. Okay, so before I go on, I'm going to start looking at our SEMs, and this should be a lot of fun, so let me set that up. This is going to be the raw part of the presentation. Has anyone got any questions at this point? Hi, WP for Truth. Hi, Maria. Hi, guys. Hi, Infidel Apostate. Great to have you, Kathy B. Okay. So, let me get these images up here. Now, some I'll just look with preview, and others I will look with different method. Okay, the first one we're going to look at is one where it actually hasn't penetrated the... let me see if that's the right scale. No, we're going to go there, and I'm going to load this into Photoshop and hope Photoshop doesn't break. Hopefully we'll be good. Okay. Let's see. Okay. All right. Okay. I think before we do this, I'm going to look at some previous presentations, just some data from it. So I just want to be fair to Alan, because in the ultra experiments where he did observe these crenellated iron-rich spheres, the challenge here is that the oxygen is just so much oxygen and there's so much carbon, and the problem here being that he's got it on carbon tape. And so what I'm going to recommend to Alan is that rather than using carbon tape, he uses copper. And this means that the signal won't be saturated with the carbon, because this carbon may be actually from the carbon tape, i.e. when he's trying to get it stuck to the carbon tape, he's depositing copper on the sample, or it's reflecting carbon from the background. And so this makes it a little difficult to see. And, you know, the oxygen may be also in whatever the carbon tape is made from, and so forth. But it could be that even in Alan's experiment, where you've got this one here, which is, look, okay, so we're looking at 21, 23. So it's right in the center kind of this ball. And he's seeing 24.02 to 41 point whatever. But it's saturated by this carbon, so you can't say for certain. So what I'm going to ask Alan to do is to see if he can run this experiment again and look to see if he puts it on a copper mounting material, whether he actually sees this 2-to-1. If that is the case, this is the most unbelievably trivial way to create these structures. And for me, it kind of reminds me more like what might be happening in lightning. As I said the other day, on Friday, Ken Shoulders said that all lightning has ball lightning. And if that's the case, then if the Hessdalen crenellated iron-rich sphere, which looked pretty much exactly like what you see on the screen and exactly the same scale as the one that we observed in the Vega experiment, which we've seen multiple of, very likely, then ball lightning has this as its magnetic core. And what do I mean? In fact, I think at this point I'm going to say, you know, what do I mean by magnetic core? Well, if you did not have a chance to look at my magnetic monopole presentations series from the middle of last year, sort of late spring into summer last year, one of the key parts of one of the presentations was this paper by Vishnevsky, and it is I've done a rough translation here, and I've walked through this entire presentation in the past, so I'm not going to go through it in great detail, but you may have recall that in the previous presentation on Friday, or maybe earlier in the week, on Monday evening, was it Monday evening? No, Tuesday, or whenever it was. I talked about the fact that Bogdanovich had referred to this guy Vishnevsky, and Vishnevsky had calculated a solution to the 1932 proposed Dirac monopole. So Dirac said that essentially under quantum mechanics you have positive electrical charge and negative electrical charge, and through symmetry you should have charges of north and south. There's nothing saying in quantum mechanics this shouldn't happen, and everyone's been looking for them for a very long time. And so he goes through talking about the work of I don't know why that's in low res. Oh dear, it's not going to help you, is it? Why is that in low res? I don't know. Maybe if I zoom out and then I do this, it's going to be better. That's better. Okay. Oh, no, it's not better if I do that. Dear. Bear with me. Okay, that's gone, so we might have to look at that in another way. I think I download this in PDF, but I don't want to do that because it'll break my machine, but I'm going to do it. Okay. Oh, now it's come up. Typical. Okay. I'm going to see if I can run it in the browser. Okay. Ooh. I'm going to try and run this in the browser. Okay. So he talks about Coulomb's law and so on. It talks about Cooper pairs and how Cooper discovered them, and that is two electrons and that forms a boson. But this is the image that I think is critical to what I'm talking about here. And so here, this is Vishnevsky in his 2008 Sochi what they call cold nuclear transmutation and ball lightning presentation. He's showing the angular velocity here, the B field, and the electrons coming into coherence, just as you saw on that 12,000-year-old lantern from Sumeria. And it comes down to what he refers to as the magnetic core. There's the magnetic core. And you have a vortical electrical field being pulled into the magnetic core. And as I'm saying, when I do believe that the magnetic core in these ball lightning and monopoles, the actual core isn't in 3 space at the time that it forms. It's kind of like the electrons are in a different state, and so it doesn't have the volume it would have. It has a much smaller volume. It's like the actual core of the nuclei, rather than the overall atom structure. And so it's much smaller, but it's not no dimension, as you might say. And as you go down here, you can see the vortex from one electron path, and then here you've got the vortex of the pair coming in. And I've shown these kind of vortices on many different samples, Hutchison and so on. And so here you can see the how it comes in, and this is your cone. And bearing in mind, I did my cone and sort of structure long before I saw this, but I have to give it to Vishnevsky. He was there first in terms of the quantum mechanical viewpoint of it. But I'm one that wants to see how things work rather than calculate how they might work. And so here's this cone, and so and that comes down to the magnetic core, and then at the magnetic core there is a kind of fixed dimension that they can get to as a minimum dimension, and then they get sprayed out from the top. And I think probably at this point I will actually show some. So it says here Sochi. Oh, that's not good. Sochi, May 2008, when this was published, and he gives credit to Brian Josephson, the Nobel laureate for Cooper pair development. And just one last shot here. This is the kind of distribution of the electron density over the period of the spiral armature. Okay, so you can see that it very much looks like a spiral galaxy, and we've seen similar structures in a maser elemental distributions in one of these vortical structures. Okay, so I'm going to show you right now a couple of slides from various presentations from my magnetic monopole series that I did in 2020, in the summer of 2020, and late spring into summer 2020. The reason I'm going to do this is because it's going to allow you to see how, for me, it was completely blatantly obvious why the thing that I saw in the ultra experiment that I did, and what am I referring to? I'm referring to this, if I can find it. I'm referring to this. Actually, it was an experiment I had already done, and I took the stuff that was left in the bowl, which I hadn't cleaned out, and I got my magnet in, and I put it around, and I got this structure. And in the center, I saw this spherical object, and this was the point at which I said, okay, that's probably a crenellated iron-rich sphere. Alan, can you run the experiment for me? And so this particular vortical structure is how we got there. This wasn't so much guesswork for me, and I'm going to show you why. I guess the first point has to be given to Lion, and this is the Lion track which I first shared on 18th of September 2017, almost immediately after I took it. In fact, it was the same day that I took it, 18th of September 2017. And I called this the paw prints of the Lion's paw prints. And this is kind of like a monopole in several orientations interacting with this cupric oxide, one of the two. And you'll notice that this particular image here is the image for remote-view.icu, and for me it's an extremely significant structure. But the thing about it is, if I go to the next frame, is that it looks very similar to the monopoles that Shishkin and Bogdanovich and Poroshenko and various other people have observed in these systems. And the thing that I liked about this is it has a hollow sphere in the center. So it's like when this collided with this surface of this cupric oxide, it consumed the material in the center, and this would be where the cone is, and this is where what Vishnevsky is referring to as the rotor. And if I actually play this, I have some frames here where I'm kind of lining it up, and in fact I will revise this and say that this actual bit should be centered in the center here as well. It shouldn't be down at this point. But this is the kind of monopole structure, but 50% of the way through it. And the reason I thought that, not only is this taking it out of our three-dimensional space, but it can actually return it to our three-dimensional space, was because of what I had observed in one of our larger Hutchison samples. And to give you an idea, this is the actual structure on the top here. This is 4 centimeters across, okay, and that is cut through, and you can see it here. So this is probably 4 centimeters, so you can get an idea of how big the monopole structure is here. And you can see the triangle here, the soft triangle in the aluminum. And there is another one here, the smaller one that I discussed in a previous presentation most recently. But first I discussed this in Sochi. But on this part of the structure, I don't know if it's very clear to you, but you can see it by going to download the slides from this particular monopole clutch video presentation. I think it's Magnetic Signature of Strange Radiation Part 3. It's this structure here, and I've blown it up, and it has this sphere and the wings. and the wings. And you will have seen this all over Egyptian architecture, but we won't talk about that right now. But anyway, the sphere, I believe, is materialized back into our free space because this monopole died here and it lost its confinement, and so it dumped the sphere here. And so that's one. Here is another sphere, and you can see the dome. You can see the dome, and it's basically identical. It's just at a different angle. You've got a perspective on here. And so what I would like to do actually with this sample, which is currently with a volunteer in New Mexico, I'd like to extract some material from here and see if this contains these iron-rich crenellated spheres, because then that would be absolutely certainly the same thing. But I don't have to do that, do I? Because right here, I've got what I said is probably the most important Hutchison sample that the MFMP has. And I call it the meteorite, and probably I should be handling it very, very carefully. But here it is, and I've done a beautiful, beautiful macro photography. And the story behind this is that this was in the corner of John Hutchison's lab, and it was below, where it was, there was some big old capacitor. And that this was just aggregating. And in this thing, you have string in there, you have large pieces of quartz, you have something that looks like a geode. And then the vast majority of this are spheres, okay? And I've only looked at this with an optical microscope, but I'm going to take some samples of this. And the next time, hopefully the next time I'm in with the SEM, I'm going to see if any of these things, which in theory teleported from the active zone in the John Hutchison's experiments to this other place and created this agglomeration, this kind of like encrustation of stuff. And if this is essentially a whole bunch of these FeO2 structures, then it's or something similar to the crenellated iron-rich spheres that you get out of the ultra experiments, I think it'd be rather special. Anyway, I'm going to put that back in there, and I know everyone's saying to themselves, why doesn't he test it and see if it's magnetic? Okay, all right. Okay, so, and I've got a bunch of slides, other slides here from Shishkin and so on. So just as a little slide here. This one here is, you've got Shishkin's one here, and this is nature, and this is from Bogdanovich on an X-ray, and you can see the kind of scale on his X-ray. This is the type of blue film you had for old type of X-rays, and you can still get it, and that's what they were using for capturing these in their experiments. Okay, so I'm going to find the next bit of context here that I want to share. I can probably close that presentation down, free up some resources. Okay. So I'm just going to run through some quick slides here from this presentation, just for those that might have missed them in the past. So on the left here, we have this very, very specific structure that is on a steel sample that was made in 1986, and we have exactly the same structure, and I can show this overlay now. In theory, maybe I can show the overlay. Is it going to show me the overlay? Yeah, it's going to show me the overlay. So it's a hexagonal type structure. It has a vortex type thing in the center, and it has this thing coming out to the side. And this is at 4 microns or something, or 40 microns or something. And this is 4 centimeters or something across. So it's orders of magnitude difference, but the thing creates the same exact structures. And so we looked at this, and you can see the structure here on this point, and the fact that it's very similar to the Bogdanovich structure that was observed 2 days after his experiment. Now I'm going to see if there's a specific slide I can show here that's more relevant. So here's another monopole on, in my view, on the top of the ball burn sample. Here's some SEM and optical microscopy next to each other. And this is another shot of the same thing. And I'm changing the focus in this shot if it's going to reveal it. So you can see that it's actually a cavity. So I'm going to the top and the bottom, the top and the bottom. And where I'm trying to get to here is that this is in physics, advanced physics. I think it may be in Nature or something. But this is what they created, these very small number of particles to create a kind of monopole type, skyrmion type, whatever structure it is. And you can see that it's essentially the same structure that was on John Hutchison's bull burn sample from 1986. And so I'm saying that this kind of like Vishnevsky type structure is focusing the material into a magnetic core. The magnetic core builds up this material, and this is what we see dropping out. And so it was not too much of a leap of faith to expect to see this in the experiments using ultrasonics, and so essentially what it looked like to me. Okay, all right, now we're going to get back on track to see what we observed on Monday in the lab in the SEM analysis. So let me get this now. Okay. Okay, right. So I'm going to bring up the contrast adjustment here as well. So here we go. Now this is going to become our money shot later in this presentation. So I hope everyone can see it clearly. And I'm going to play around with the contrast so you can maybe get a better idea of what we are looking at here. Now, why is this very interesting to me? It's interesting because we have a cone with a dip in the top, and we have a pit with a hill in the top. And in this case, it looks like it's got a hexagonal or pentagonal structure on it. And if you recall from my own examination on other things, it tends to be a hexagonal structure. Okay? And that points me to something that's vortical in nature. Right? So the interesting thing about this is that this is very early in the formation, and these things form extremely quickly. If you look at the videos where I'm showing them live, you can see that these form very, very quickly, and then they're very stable once they're formed. And I'm going to show you some images from previous blog posts so that you can hopefully get where I'm coming from. I think probably this blog is probably the most significant to answer what we're going to need to answer today. And it's called Ultra Fingerprints. And you can see the cone here and the pit, and this is the hexagonal structure here in the center. It's maybe not so obvious, but you can go and have a look at this. And the other interesting thing is you have these kind of rings that come from the top and the bottom. And in this one, it's a GIF animation, and you can see things spinning around very, very quickly when they get to one of these structures. And they kind of come and hit the cone and spin around the cone. And the pit, sometimes you can see things going into the pit. Now, this for me is probably the most important video I was able to grab. And what happened in this video is, and what you're seeing here, is this is a fraction of a second after I turned off the ultrasound. Okay? And so something was spinning around in here so quickly that you couldn't see it. Okay? And then as soon as the sound came off, you got a toroidal bubble. A toroidal bubble that then goes into a spherical bubble and then goes off to the side. A toroidal bubble structure. Okay? And here I've got the frames broken down. And it's easier probably if you look on your own computer in your own time. But you can see here that it's just a blur in this frame. Okay? And then you come down to here and then you can see the torus bubble here. Okay? The torus bubble. And then over here you've got the bubble peeling off, and it's peeling off more, and it's starting to become spherical. And over here it's basically a sphere in the center there. The sphere's moving away and the sphere's gone off down here. Now, I believe this will happen pretty much every time, and therefore this will be extremely, extremely replicable to anyone that bothers, essentially. Here is something that gives you an idea of how you could get carbon deposits on there and the silicon deposits. Obviously, aluminium has often got plenty of oxygen on it, and you can see some scales here. And down here in this one, I like this one because it may not be clear to you, but this is the pit and this is the raised point. And what happens is the bubble moves around, and then it puts a helical beam into the center of this peak as it drifts by. It like fires a helical beam. And I haven't actually shared these because I haven't had time, but I've actually got helixes going through the water. And so we'll come on to that. Now, here is the thing that I think most closely matches what you're seeing here. Okay, you've got your, let's bring up our contrast here again. We'll do that. So we've got our kind of hexagon here, which is raised in a trough. And then we have the pit, and here we have the cone, and then we have a pit in the top of the cone. And so this is kind of what you're seeing here in this optical microscopy image that I shared previously. And you can see it multiple times. So I like this shot because you've got the pit with the hexagon structure in the center, and that itself has a raised bit. And over here you've got the cone with the dimple in the top. The cone with this one's hexagon shaped, but it is fairly flat. This one is the pit with the raised bit in the center. Okay, and the hexagon shape around that's a little less obvious. This is the same kind of structure, but on a palladium coated steel vibrator plate from Roy-Shinomasa. And you can see the vortical structure here that we were talking about, and I talked about how that transmuted matter a number of times. And here is the same structure out of Alexander Parkhomov's 225-day reactor, but this in itself is from in my view, a magnetohydrodynamic structure, a kind of like eddy current type inspired structure rather than one that's come from a hydrodynamic structure. But the hydrodynamic structure, as I'm saying, and I think it'll become clearer, there is charge separation going on, and then you've got things spinning, and so that creates electric fields, and that creates some movement of material, and I think that's what causes what we see. So you can go and have a look at all these different experiments. In this frame here, you can see this is our cone, and this is our pit, and the vortex is going round into the center of the pit, and in this case, it's going round clockwise. It's going clockwise into the pit. In this one, this is the cone, and it's going anti-clockwise. Yeah, maybe you can see it. Maybe you can see it in a minute. There's actually a section that's cut off here in this frame here, and this is a cone that's cut off. Okay, this is from some other part in the material in the foil in the experiment. And so it's spinning around anti-clockwise this way, and this one in the pit is spinning around clockwise. I used a laser pointer to highlight the features in this one. And it's this kind of structure that you see here that was first picked up by David Boutelier in his experiment and he picked them up like this with a magnet. And this inspired me to do the same experiment the following day. And that's when I saw this hexagon structure with the sphere in the middle, and I thought that that was what we are going to see the crenellated sphere with. So again, you've got the kind of S shape here on the peak that he identified, and we'll come on to some other stuff in a minute. Now let's go back to our SEM analysis. And we've got some extra resolution in here, so we will, if it's still going to allow me to use it. It's not going to allow me to use it. Oh, great. Here we go. Jackanory time. Let me get rid of Safari and kill that resources. Okay, maybe it's going to give me some joy now. No, it's not. Okay. Okay. Good. We'll have to take a break. Wait for the computer to cool down. Right, so actually I have this image here which I drew as a proposal, and it's here, and I've cut through my aluminium virtually. I'll get rid of my mugshot, and this is the flat plane of the aluminium, and this is the pit with the raised bit in the center, and then it goes up to the raised cone, and then they've got the bit in the center, and then down. Okay, now we know that the what did we show in the last up here? We showed that in the pit it goes round clockwise, and in the where is it? Where is it? Pit goes clockwise, and the other one goes the other way, wherever it was. Maybe it was below that. Pit goes clockwise. You need to look at the right frame on this. You'll see it after a while. Anyway, the spike goes anti-clockwise. So if we're looking at our pit here, our pit is going clockwise, so the vortex is going clockwise into this. Or maybe it's going anti-clockwise underneath and it's pushing the center up, and it's actually like this. Okay? And so it's going anti-clockwise underneath, and you've got a clockwise thing above. Maybe. Like I say, I'm not settled here, and people can have, you know, there's a whole blue ocean of opportunity in understanding this. So what we have seen is that we've seen when we turn the sound off, we have a toroidal bubble in the middle of the hole, as it were. And I'm speculating that you see there's an unseen one on the opposite side. Okay, there's a toroidal bubble under there. Now these bubbles are actually also cavitating the whole time in sympathy with the sound. So it's quite a complex phenomenon, but simple and beautiful at the same time. And this is clearly creating a pair of vortices, which I believe are cohering matter at the center of these peaks and stuff. And that's what we will see. Okay. So let me go and get the next thing that I want to show you. Has Photoshop come back to me? Oh, I see what's going on. So Photoshop will not allow me to. It will not allow me to have the what do you call it? The levels adjusting at the same time. So here we can go. You can see this with a little bit more fidelity here. Okay. And to a certain degree, you can almost see the vortical structure on this. Yeah. It is a hexagon kind of shape. Okay. But it also has a vortical kind of nature to it. And I imagine that if we could look at these things closer, we would see more of that. This mostly looks like a pit. Not so interesting. Okay. So we have quite a few images to get through, so I'm going to do that now. And I'm going to dump a few of these slides. Didn't want to do that. Where are we? Where are we? Okay, here we go. Right, let me see. The next one I want to show you is next one I want to show you is this one. Is it that one? No, this one. I know what I'm going to do. I'm going to make those bigger previews so I can actually see what I'm doing. Okay. So in this next one, he says, hopefully, in this next one, we've actually got the thing progressed a little bit. So in this one, we don't actually see any damage to the foil. It's just embossed and debossed. Embossed and debossed. Okay. In this one, however, we actually see that this one, it still looks relatively intact down here. Maybe there is a hole forming in that. Maybe there's a slit there. Certainly, I think probably if we adjust our levels here, auto, maybe you can see an S of the vortex here, and this S means that it's going round. In this case, this is going round clockwise. Okay, so maybe this piece of material is upside down. I don't know. But you can see the S there in the center. So it probably is a very little hole there. Okay. And I'm going to go and overlook on here. And you can see that this one actually is quite broken. And we've got actually a fracture that comes all the way down here. But the fracture is born out of what's going on in the base here. It's not like the fracture came down here and made a hole here. No, this forced this fracture here, in my view. But what do we see? We actually see a kind of twisted fiber coming through this crack. It's kind of vorticey twisting this way. Yeah. So what do we have? This is going anti-clockwise in this case, and this is going clockwise. Okay, it's going spinning around this way. So we might be looking at the underside or the top side, depending on which perspective it has. And these things can be nailed very readily by people that wish to bother to do the experiment. Okay. But anyway, what we're going to look at is what this twisted structure is comprised of. And I think it's going to be very interesting. What do you think? I think it's going to be very interesting. And this is where I've already got Excel open, so hopefully it doesn't cause me undue problems. More than... Okay, so... It's all a bit of a mess, this, because it's very raw. But this is the way I'm bringing it to you faster. Okay? So you're just going to have to live with it being a bit raw. It's kind of like you are having an inside track on what's going on. So it's not such a bad thing, is it? Okay. And I've actually got a better image of that particular structure, so... Here, we will look at that, and hopefully it doesn't make my machine die. Ooh, that's rather nice, even if I say so myself. Right, here we go. Look at that. So here is. I haven't actually looked at this image. So look at this. It's actually rather fine as it squeezes its way through the core of the vortex. There we go. Isn't that nice? There you go. You're looking at this at the same time for the first time as me. Isn't that nice? It's like a big fat kahuna, isn't it? Oh dear. Right. So we're going to dump our cigar over here. There we go. We'll dump our cigar. And we will get up our analysis. And first off, the pit is 82.4 microns. So that's kind of like the defined area of that pit. And then we have a whole bunch of images, which is not going to be very easy to see here. So I'm going to save this image, save picture, and we're going to look at it in another means. So I'm going to call this cigar. Why not? Right, where have I put cigar? Where's cigar? Where did I paste that now? Oh dear. I'm going to pay attention now. I'm going to do this again and pay attention to where I'm saving it. I did it in, okay, ultra crop circle, so why can't I find it? Oh, I know why. There we go. Ta-da. Okay. Well, that's not any better, is it? Okay. Sorry, that's not going to help us a lot, is it? I don't know why. Why is that not helping us? Oh, I've not saved it yet. I do love the way Excel saves something at the resolution you're previewing it at. Not very helpful, Microsoft. Give me a second. Talk amongst yourselves. Yes, I want to replace the very poor resolution one you gave me before with something that's useful. Thank you. Okay, all right, that should be working now. Okay, all right. No, it's still sending me something terrible. Oh dear. Okay. I'm going to ask people to use their memory. Oh no, I'm going to do a screen grab. Why not? I'm going to do a screen grab because I can do that. If Excel's not going to allow me to save it properly. Let's do that then. That gets round that program's ineptitude. Right, okay, right, okay. No, I don't want an update now, please. All right, sorry. It's going to look lovely, honest. Okay, all right. Here we go. This is what I've done for you. Right, so we have Spectrum 1, which is kind of inside the bowl. And it is what? It is by atomic percent, 78.5% aluminium, 3.78% oxygen, with a little bit of carbon and nitrogen, and by weight it's as you can see there. So can you see that? Maybe I can zoom in and make it a little bit clearer. Okay, so this probably is going to work for you guys. So that is Spectrum 1 here, which is on the bowl. Interesting, it hasn't got much oxygen on there. It's not seeing the oxygen so much. It is mostly aluminium, which is good. This is aluminium foil. We are seeing aluminium. Right, Spectrum 2 is in the base. Now note that the carbon is 17.36. What is the base of that? And actually it's less. And in fact, it's even more aluminium. So in Spectrum 2. So on the base there in this case, it's even cleaner aluminium. Now Spectrum 5 is this structure here, right at as it's emerging through the base of the slit. So I actually haven't looked at these very much, so you're going to see, oh hold on, it's giving me Spectrum 3. Spectrum 3 is kind of this dark area on here, here, Spectrum 3. And Spectrum 3, oh hello, look at this. So the aluminium, let's look at the atomic percent, keep it the same. So the aluminium has dropped from the Spectrum 2 is here, and the aluminium is 94.06%. And down here we have on this area here, spectrum 3, the aluminium's dropped 34%. And carbon's gone up. So this looks like it's forming a carbon tube. And we've actually got notable amounts of silicon forming. Some sulfur, some chlorine, calcium even. Look at that. Calcium. So that's quite a lot heavier. In fact, chlorine's heavier. In fact, if you take aluminium and you add, is it 2 alpha particles to get to chlorine? So sodium, no, we've not got no sodium there. So we've got chlorine without sodium. So that would be 2 alpha particles, would it? Aluminium 27, sodium 20, no, it's maybe it's just 1 alpha particle on 2 aluminium. Anyway, calcium's heavy. And but of course you do get calcium in tap water, so this could be just a concentration thing we do need to bear in mind. But that's not always necessarily a bad thing as well. These experiments do need to be run with deionized water and a very clean chamber. But what we are seeing here is something a little bit more interesting. So what do we have in that spectrum 3? Spectrum 4 is where? Spectrum 4 is right at the end of the tip here. Let's see what spectrum 4 is. Spectrum 4 is much less aluminium, much more calcium. So right at the tip here, we've got a much more calcium. That's 27% by weight, and by atoms, it's 21.51%. Aluminium's gone down to 9.71%. It's basically not there. We've essentially got calcium oxide. Okay. So, you know, you could argue that this is contamination, but you have to look at where it is. You have to look at where it is. It's the actual part of the vortical jet that's coming through the center of this structure. We've got chlorine there. We actually have some sodium here, but it's not in a sodium chloride ratio. So the chlorine could be synthesized from the aluminium, the silicon, and so on. So and plenty of carbon there as well. So that is spectrum 8. Was that spectrum 8? Oh, what am I talking about? Spectrum. This is spectrum 5. This is spectrum 5. Where is spectrum? Spectrum 5 is this bit down the bottom. Sorry. Spectrum 5 is the bit down the bottom. I'll get it right in a minute. Spectrum 5. Okay. So the spectrum 5 is a lot of calcium and oxygen. Okay. And what is that's still spectrum 5 on the atomic percent. Spectrum 6 is this dark area here. It's probably a lot of carbon. Is it? No? No, actually. No, really? Spectrum 6. Well, it says that's quite a lot of aluminium there. Argon. Interesting. Interesting. And spectrum 7 is where? Spectrum 7. I can't even see spectrum 7. Spectrum 7 is that point there. And that is some calcium, very, very little aluminium, almost magnesium. We've got like a lot of magnesium. So that's atomic percent, 8% magnesium there. And spectrum 8 is the end of the line. Oh, that is 33% by weight. And my colleague has been mixing these up with the weight and the atomics, moving them around. So 21.18% at the end there. Anyway, what we can say is this is not all aluminium. We're seeing other elements form, and they are forming preferentially, it would seem, let me move this down here, in this structure. Okay, so from my point of view, I think that you could argue that it's concentration, but the point is that it's all kind of growing off here. It's off this feature that's coming through here. Now, if this thing broke off and went somewhere else in the experiment, then you would obviously see these things that have been synthesized elsewhere. But this is why I'm interested in seeing what is happening at these actual parts of the vortex. Right, now let's have a look at the next one and see what I want to show you. Okay, next one with the analysis. I think actually I've got the reverse side of that, have I? No, not that one. Yeah, I've got the reverse side, which we'll have a look up close. just for the sake of it. So yeah, so you can see here there's, yeah, maybe, I don't know. I think I actually analysed that. Let's see if I did. This structure here. Give me a sec. Are you bored yet? It's going to be some nice reveal at the end, if you can make it there. Nope. 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 Okay, so I have an image here for this. Okay. I'm going to try the same approach this time, because it's just quicker. Right. Okay. Oh, getting a method here. I'm not mad, let me out. Okay. Right. Okay, so this is our top of the other side, and I am looking at the area around the top here where it is affected. And we have spectrum 10 through 14. So spectrum 10 is the first up, and that is kind of right, this little bit here, where we have this kind of S shape here on the kind of like center of that bit. And this is 29% carbon by atoms. Aluminium's down. Hello, what's going on here? What is that? Silver? Silver? Are we making some silver? Really? Really, I don't believe it. Really? Not overly convinced. Maybe. It says AG, but it's not overly convinced. No, there is a peak there. There is a peak. Interesting. Okay. It seems to think that it's making some silver. But it's below 1% atomic, so it's not certain of it. But by weight, it's 1.28%. So, you know, not too shabby. Making some silver, if we are. Like I say, this experiment is so easy you can verify it yourself. It's so easy. Oh dear. Right, but the big thing is we've got carbon and we've got some silicon coming in there. Nothing else. Sorry, silver rather. So that was 10 already. Already we're off to seeing something interesting. 10, 11. What have we got in 11? Wow. Okay, 11 has got all kinds of things going on. So 11 is where? 11 is kind of like up on the crest of this. No, it's not quite on the outside. It's still within the set. It's on the edge of the inside hexagon, which is actually clearer on this fuzzy one than it is up here. Okay, so we have what? Lots of carbon. Absolutely bucket loads of carbon. It's approaching 50%, and less aluminium atoms. Silicon is creeping in there. Sulfur is not worth talking about. Chlorine's low. Argon, it's interesting, there's argon. Some potassium and some calcium creeping in there. Okay, so that's 11. Where's 12? 12 is on the outside of the affected area. So 11, what do we see? It's more aluminium in this one, and the rest are just below threshold kind of levels. A little bit of silicon and some carbon build-up. Okay, and then 14 is a spot over here which is quite bright, so let's have a look at what we got there. Oh, hello. 12 outside there. Really? That's 11. 12 is, no, sorry, 11 was there. 12, 1.12% by weight. Is that more? Is that more or less? 0.24. What was the other one? 0.26. No, but we've got 2 places that are reporting silver. Yeah. Okay. 12. Okay. And 13 is right on this sort of structure here, which is quite interesting. And that's got more argon. It's not very interesting. No, it's mostly aluminium. And then we have 14, which is this kind of fleck on the outside here, which is kind of like everything. Oh, wow, hold on, there's a lot of calcium. So this might be something from the water, which is kind of crystallized there. Maybe. A lot of carbon still. Maybe calcium carbonate. What is it? CaCO3, is it? Well, no, that's O2, isn't it? No, it's not calcium carbonate, but anyway. All right, so that's that peak. Now we're going to have a look at another one of these structures. Yes, Corky, when gold becomes trivial, we are making progress. Yes, well, as I'm saying to my good friend Alan Goldwater, we should run these at different run lengths and see if you're getting heavier and heavier elements. And you might find that there is a amount of energy you need to put in, the amount of coherence you need to get to a particular target element. Wouldn't that be nice? Wouldn't that be nice? Just with sound. How funny. Oh dear. Always been sitting there right for us to discover. All of this time. Just sound. Let me just get rid of this whilst I set up the next shot. Okay. I've got a mosquito drinking my blood. Okay, I've got another one where it's kind of breaking through, but this time it's breaking through the peak rather than trough. So we'll have a look at this one. So here we go. Kind of like the angle on the electron beam illumination of this. Again, you've got a very, very clear hexagonal structure here. Well, pentagonal maybe, pentagonal. One or the other. You can see that it's got the lobes, so you've got a curve around here and a curve around here. Bit like our pomegranate that we saw in the Vega experiment. And so down here we've got a very clear demarcation on the top, and it's cracking. And we've got a bit going over that way, and it's kind of an S. So this looks like this was going around anti-clockwise. So maybe it does always go anti-clockwise around the peak. But this does depend, because on these samples we looked at the bottom side and then the top side. So without me getting the registration right on that, I might be looking at one or the other side without realizing it. But definitely I would argue that this is coming through pretty much the center of the center. And so I don't think this is detritus that fell here. I think that this is material that was in the center of the vortex. Okay. Very, very clearly demarked. It's like a flat top. And in fact, if you get down to the center of this, you've actually got a little peak in the middle there. So maybe this is a structure that was driven with a little bit more energy. Don't know, but we are going to first look at what is in the center of that. Now, I don't know whether I maybe didn't take a image of this, but it's nice high resolution anyway. So we're gonna go there anyway, I think. I'll pull that off. And I'll put that over there. Let me just arrange this for you. Okay. All right. And then we'll go to the Excel and not that. Yeah, that's the one. Okay, good. Right. It's a bit of a mess. Can I get better than that? Yes, I can get better than that. Okay. Okay, give me a sec, I'm nearly there. Okay, so have a look at these now. So we are going to be looking at spectrums 22 through to 25 in this analysis. So 22 is on the outside, so it's here on the, get rid of my mugshot. It's here on the outside, so not in the darkened area on the peak, the flat top, or the dimple. It's on the outside here. And that is mostly aluminium, a little bit of argon, and a bit of carbon. Then atomic percent on spectrum 23, which is on the top here. It's somewhere, it's just to the right of this little dark mark here. Here. And this, hello, we got silver. Is it really silver? No, it's still not calling it silver. Now this might be a band overlap, but there is a peak. But you know, you kind of would want to maybe push this a little harder and see if you get more silver, but maybe it's not. Maybe it's a band overlap. Okay. So now we're looking at spectrum 24. Oh, hello. Hello, what's happening here now? We've got some iron coming on. We've got some iron forming in my 90-second experiment. Isn't that interesting? We've got aluminium's all the way down to 7.59% atomic. Silicon, look at that. Just like Mr. Huang. We have 8.47. In my view, the silicon is a precursor to getting the iron. Because that's what you see in ball lightning. Okay, so we have the silicon. Wow, your carbon's up at 46.22 in this structure here. And the silicon's going strong at 8.47. But for me, the big win on this particular sample is we are seeing 1.27 aluminium. So maybe Alan got his iron crenellated spheres because he was running the experiment longer. Or maybe if you've got more energy in one particular structure, then maybe that's what I would get my magnetic thing from. But if you ran it for longer, you would have more magnetic crenellated spheres. But I believe that we are seeing here with this one that's a bit more damaged, that we are seeing more iron here. More iron. Okay, so we've got one more spectrum. This is 24. What's 25? 25. What's 25? Oh! Look at this! Look at it! The carbon's gone down. We have aluminium's gone down, I think maybe. What do we have here? We had aluminium was 7.59. Or maybe it's about the same. 7.59. It's about the same. But silicon is 13.3. Oh no, we're on weight. Oh, she's mixed them up. She's mixed them up. No, about the same. About the same, but 2.72 on the... Oh dear. She keeps mixing the tables around. So we got... that's weight percent. It is relevant to look at the weight because it is a heavier element. So silicon's 8.4, iron is 1.27, and here we've got silicon's 8.4, but the iron is 2.72. 2.72. What was it up here? 1.27. Okay, so the kind of brighter area on this is increasing the amount of iron, and in fact, weight percent. Is that right? Weight percent on spectrum 25 is 8.61. So this is nearly 1/12 of this particular area is iron. Okay, and it's in this structure. It's not randomly placed. It's in the center of the vortex. Okay. Okay, so I think we're moving in the right direction. Are we? Are we moving in the right direction? I don't know. Yeah. Okay. Let's go one more with this. Kind of like this one. We're going to do this one next. I think we will do this one next. Let's see. Right. Okay. And I'll take this one. This one's interesting. I think it's slightly different in its look. Okay. Okay. So this one actually, it doesn't appear to have broken through. But yeah, I can see it's broken through. Okay, I think this actually might tell us quite something interesting actually. Okay, so here we go. So this one looks a little bit softer, but I think it's just the way the electron beam is hitting it. Maybe I can. Okay. And I'd like to do some spatial awareness of where these little particles are, which I have to say they look quite familiar. Okay, so right, there is a crack at the bottom here, and I wish I'd actually looked at this. So there's a crack here, and this kind of seems to be failing as well. There's crystals here, but it's almost like it's sloshed around and it's kind of like deposited something here. Now, this to me, I would say, and I'm riffing here, but I would say that this is the influence of coherent matter interacting with the aluminium and actually in the process of synthesizing other elements when the music stopped. So that's that. And the other side, it's kind of almost got the same, but kind of like maybe this looks like the other side, but if you could see the underside, and this vice versa. But this looks, I've seen this before, and you know where I've seen this before? I've seen this kind of thing where you've got one element blending into another. I've seen it in the indium that we first found when Alan Goldwater said, I've got to clean the indium that we want to use as our control for the indium that we put in the Amasa vibrator system. And he put it in for a few minutes or a minute or whatever, and gave it to me, and I said, Alan, we've got like 3 explosions on this aluminium, on this indium rather, and it's blending from indium through to silicon. How is that even possible? And through carbon and stuff from your indium. It looks like a plasmoid's moved out from the end. These are quite nice little crystals. Look at these. These are fun. What are those? Look at those. Interesting. Okay, so let's find out what we have here. Let's find out what we have here. So give me a sec to set it up. Okay. Right. So I think there's three structures. Maybe I don't know whether I grabbed that. I think I only looked at the top of this, but there is this other structure over here, which looks to me like an Evo splat. Yeah, you've got some light thing in the middle and then this splat around the outside. So I think we're going to also look at this, because this is something, you see these things moving around in ultra experiments and interacting, and I believe that they are coherent matter blobs that are able to move around in the thing. And I think one of those in the experiment, and I think that hit here and did this blob. So we'll have a look at what that is. If you just give me a sec to set this up. Let me see what I had in the Excel. Okay. Getting there. Nearly there. Okay, we'll have a look at the things on the top first. Okay. And okay, here. Right. So we are going to be looking at spectrum 33 through to 37. 33 through to 37. Okay. So, okay, so 33 is where? So not very clear. I think it's this nodule here, which is under my face, so I'll get rid of that. This nodule here, okay? Maybe I'll zoom into this a little bit closer. So we're looking at this nodule here. Yeah. And so 33 is 45%, 46% oxygen, 23%. So that's almost aluminium oxide, actually. It's actually made aluminium oxide. But we have some phosphorus that is not really at detectable levels. But we have sodium at detectable levels, potassium, chlorine. So we've got some salt making here. Now, is this really salt? Is it something that's in the water? Is it contamination? If it's not contamination, then if you have water crashing against a shore that has aluminium-rich rocks, could that be some way in which the salt in the oceans became there? And if so, that is unbelievably important because we are salt creatures. We are salt creatures. Inside our blood, we are salty. And it could be cavitation that is producing the salt from the elements that are necessary for life. So I think that, we need to consider that. So you've got potassium, chlorine, and salt. And these are things that people are observed synthesized. But you do have to bear in mind it might be contamination, but it's in this structure, which is on the top of the vortex, okay? It's not random, okay? It looks like a lot of it has been made here. So let's have a look at the next one. So atomic percent, that is 3.55% chlorine, and sodium is 1.38, and potassium is not a lot. Okay. So spectrum 34, which is I think it's on the top. It's like kind of like this area of this floret on the top here. That is atomic percent, mostly carbon, very little aluminium. We've got silicon 1.3, molybdenum. Molybdenum? Seriously, no. It's not molybdenum. Molybdenum. It's molybdenum. No. Yes, it's molybdenum. Molybdenum? What? Okay, I'm going to have to do the spectrum overlaps for this and confirm this, but if that's molybdenum in there, and that's not, that it's definitely saying it is, and that is by atomic percent, 0.83, so by weight, that's going to be a lot. 4.43% by weight of the top of this floret here is molybdenum. That's crazy talk. Okay, I have to look for spectrum overlaps, but okay, that for me is the biggest shock so far. Molybdenum. I'm quite happy I'm doing this with you real time. Look at that. Molybdenum right in the center of the vortex. Wow. Okay, so I can't even remember where molybdenum is on the periodic table. I'm so excited. Let me have a look at that. File, new tab. It's quite far across. Molybdenum. There! It's gone beyond zirconium. Wow, because if you take 2 calcium oxide, that makes zirconium oxide. So it's basically yeah, okay, so if you take 2 CaO and you fuse those, you get 1 ZR02, I think, or something like that. It's Bolotov, I think it was, that did that experiment, and then it's added an alpha particle to that. That's crazy. Molybdenum. You can really see how, with very little effort, using aluminium perforated foil in a hydrosonic pump, how Leclerc and his partner was able to synthesize every element in the periodic table. When you are bringing the mountain to Muhammad, or whatever I should call it, and you are looking at this, this is the point where it's concentrating energy. This is the snowball rolling down the mountain. This is crazy. I have to check, but if that's making molybdenum, that is really serious. That is really serious. Oh, it's just such a pleasure to share it with you guys. Of course, I might be wrong, but there it is. It's 4.343% by weight. Madness. Absolute madness. Where's 35? Okay, so what I've done now is I've gone down to this splat structure down here. And I've got it down here. And I'm just looking in the center of the splat structure and on the kind of substrate to the side. The side of the splat. Okay, so 36 is to the side. So 36 is, yeah, it's kind of expected. Oh, there's a lot of sodium. Wow. Wow. No, seriously? Oh, I think that might be a crystal there. We'll have a look at that close. Yeah, it's basically sodium chloride, is it? NaCl. There's sodium chloride. There's a crystal of sodium chloride there. That might be what all those crystals are everywhere. And if that's the case, is it making it or not? I don't know. We've got this rod here with something with, anyway. And what is in the center of 37? 37 has mostly carbon. It's a carbon splat. Yeah, so that probably is a Evo that was moving around in the water and dumped carbon, bit of magnesium, almost not barely detectable aluminium. Silicon, phosphorus, sulfur, but these are all too low. I think if you looked at the spectrum, it would be ignoring most of those. Spectrum 37, yeah. So it's saying it's mostly carbon. Chlorine, magnesium, calcium. Yeah. Oh, it's definitely saying those are there, but no, for me, this sample top here, the top of this crest, let's have a close look into that. So we're actually looking at the top of that floret, which looks like the very, very, very top of this feature. Yeah, no, I'm not going to look at it that big. This structure here, right in the center of this structure here, we are apparently, although I'm having difficulty believing it, it would say that where is it? Oh, no. Right in this floret. We are apparently creating or synthesizing molybdenum. Where did it go? Where did it go? Down here. I'm going mad. 36 it was, wasn't it? No. Iron. Am I even on the same thing? I'm not even on the same thing, am I? Yes, I am. 34. Spectrum 34. Yeah, molybdenum. That is absolute madness. Wow. And the potassium is much higher here as well. Wow. Okay, so onward. Let's see what we have somewhere else. Oh dear. Okay. Let's pull up the next one. I really like the next one because this kind of shows us exactly. Well, I'm going to show you the splat up close. So let's show you the splat up close. Open with, so you can really get an idea of what this feature looks like. And so this is the splat with the carbon and the beautiful salt crystal over to the side. So there we go. That's our splat. So it's a 1, 2, 3. Is it 6? No, it looks like 5 to me. I think it's a 5. No, it could be 6. It's just got the splat here. Maybe it came in from an angle. It looks like it came in from an angle. I don't know which angle. But it's definitely got a circular section in the middle here. What is that size? 10. It's definitely 5 microns in the center, the hole. And yeah, It's 10. It's kind of 20, it might be the 27, that kind of scale. But look at that salt crystal. It's absolutely, it's comically perfect. There we go. It's like a play school chemistry experiment. Someone's dropped a notepad. Can they take it off, please? Get rid of your... Don't put your notepad on my experiment. Okay, there we go. All right, let's have a look at something else. Yeah, I need to look at... So, Anbeck, maybe the molybdenum, but as I said... I think it was Bolotov. He found that if you get calcium oxide, 2 calcium oxide goes to 1 zirconium oxide, and then if you add an alpha to zirconium, you get molybdenum. In my understanding. So, right. Yes, just need some vinegar. Very good, dog, Gordon. Yes. Now you got me salivating. I want to go down the chippy, which is not really something you can do here easily. Stop it. Stop it. Okay, so I've got a little bit of a fondness for this next one, which is the last of there's a special, and then there's the last one, and then I've got my exciting reveal for you, and then I'm going to ask you to help me. So, let's go here. Blah, blah, blah. Okay. So I like this one because it's very well defined, and it shows a little bit more of the sort of progression of something being destroyed. So here we've got a crack running between the two, so there's obviously some sort of fracturing going on. But if we look at the this one down here, well, hold on. This kind of ties back to the Bin-Juine Huang, the Professor Huang's work. You have an S here. So this is a pit, and it's going around counterclockwise. And it has the sort of round bit taken out of the center. So it's a little bit more open than Professor Huang's one on his copper. But what I love about this, is that the transmuted material is actually blending into the aluminium. It's blending into the aluminium at this crease. It's blending into the aluminium, yes? And it's blending into the aluminium. It hasn't broken away. It's blended in the vortical structure. And if we come up to the other side, so this is going round counterclockwise, and this one is going round clockwise. And again, you have a feature that is in the dead center of the vortex. I don't think we could be any more clear. It could be concentrating stuff in the environment, but let's see what we have here. So this is a very, very clear structure. And it's, again, it looks like it's blending in, and it's kind of broken away, but it's kind of blending in. Definitely, this is not something that's just fell here. It's actually part of the vortex. So this one for me is just, it's just beautiful. It's just totally beautiful. The interaction and the registration with it fitting in. So let me just pull up what I need here. Have I got any close-ups? Okay, so I have a close-up of, maybe I only had time, I might have only had time to do one of these. which is a shame, but anyway. The experiment's so easy that people can do this all over the world very, very quickly. So, I mean, there's almost no excuse, to be honest. No excuse. I mean, I have said this since the first time it was proposed in September 2019, but fortunately some people had a go. they found a spare $35 and half an hour of their time. Okay. So what this is pointing to is exactly what I said in my OCCF 22 presentation, where I said that Mars's vibrator plates are effectively able to create micronutrients. And because they're gentle, I wouldn't expect them to easily create extremely heavy elements, but micronutrients. And this is essentially what water is doing when it's going down a stream. It's producing cavitation, and because the rocks are stuck in place and they will contain things like aluminium, and the water's going past, there will be a cavitation spot, and then that will be synthesizing new elements that will be going down the stream. The stream water, running water, is much more interesting than just the rain that produced it. And that is the same if you've got water coming through cracks through pressure, going through the mountain. Your minerals are the minerals in mineral water leached from the rock, or are they a combination of leaching and synthesis through cavitation? Is the rich minerals that come out of hydrothermal vents, are they in part due to cavitation or just leaching of minerals? Is the gold that comes through these kind of hydrothermal vents and gets deposited in plains, is that actual gold that's being dissolved and silver that's being dissolved? Or are these elements that are being synthesized by the actual cavitation process that's going on as that hot water is coming up and working its way through those cracks? Think about that. Okay. Oh, I have got the other one. Good, excellent. I'm happy about this. Good, excellent. Ha. Oh, what do we got? What do we got? Okay. Gonna put that in preview because I can see it better. Right, just got two sample areas in here, and let's have a look at them. We have spectrum 42 and spectrum 43. Spectrum 42 is this bottom lump. What have we got there? It's spectrum 42. Hello. Okay. This is that what? 54% atomic boron. Boron? Really? I mean, there's barely detectable aluminium. Boron? That's got to be synthesizing that from hydrogen. Really? Okay. If this is boron, then it's synthesizing it from hydrogen, which is proton chain, which is shocking. So I think this must be contamination somehow, but it is right in the center of our vortex. it's a little bit difficult for me to accept, but it is what it is, what we're seeing here. So my first thought is maybe there's some sort of cleaning fluid that maybe the person that handed this to me is in there, and it managed to pick up a particle, but it is there and it's blending into the aluminium. It's blending the boron into the aluminium. But 54.17% by atomic weight, and then the next thing is carbon. So boron is 10 and 11, carbon is 12. Okay, so that for me is a shocker. Like I say, the molybdenum I can't believe, really. Maybe I can get there through Bolotov, but the boron, that for me, that you have to be synthesizing lithium and then fusing lithium isotopes, 6 and 7, is that right? No, 6 and 6 is 12. No, that's not right. It's tough to get to boron. I mean, that has to be proton at a first guess chain, and that's most of what it is: boron and carbon. And carbon is like you just add a proton to boron, right? So, okay, that's what it's saying. Okay, and what is spectrum 43, which is kind of more of the same, but let's have a look. Spectrum 43, boron again. There you go. Okay, and a lot of chlorine. So I don't know. I think we need more people out there doing these experiments with SEMs to see if you can replicate this kind of observation. That for me is a bit of a shocker. This is almost more of a shocker than and I would suspect that this is some form of contamination somehow, somewhere. The molybdenum could be synthesized. I'm more easy of it. As shocking as that was, I'm easier. I find an easier time to accept the molybdenum. Okay. All right, but I mean, it's just all weird in its own right. Okay, so let's have a look at the other part of this. So I have, where did I put it? This part. I've got this somewhere. So give me a second. Okay, we've only got 2 samples on this. We've got the background and the peak area, so we'll just see what that is. Like I say, I'm looking at this the first time with you guys, so I kind of like that, actually. It's like my surprise is your surprise. Okay. Okay, so we have spectrum 44 and 45 in this one. And let's have a look at see what we have. 44 and 45. Okay. Boom. Okay, so 44 is the light area here, which is kind of like the center. You can see it's kind of like a half. It's a broken hexagon. You've got one part over there, and you've got one sort of kind of half of it there. So 44 is mostly carbon. Well, 42% carbon. We've got some sodium there, 5.25%. Magnesium. The aluminium's down to, we're on weight percent. Let's go on atomic percent. 44. Yeah, so 57.3% carbon, oxygen is 23%, sodium 3.71, 2.89 on the magnesium, aluminium is all the way down to 5.26, and then we've got some chlorine, potassium, calcium. Hello, we've got some copper. Anyone order some copper from aluminium? Really? Copper? Okay, all right, that's heavy. So 1.55% copper here, right? So we can start with cheap old aluminium and synthesize some copper. That would be madness, absolute madness, because there's a copper shortage in the world, but there's bucket loads of aluminium, right? It's the third most abundant element in the crust, right? But copper, wow, that's making copper? It's making copper? Wow. All right. So I completely accept 100% that Leclerc was making every element in the periodic table. I completely accept that with the evidence that I've seen tonight, with my first look at a short run experiment, this is from the exact experiment that I did to do the 4K, how to do a quantum coherent torsion field reactor experiment. And we're seeing heavier than iron elements in the form of copper and molybdenum, and potentially less likely for me, it's more difficult for me to accept, but we are apparently seeing boron made, which, you know, I need to look at that, but I can't see how you're not making that without fusing protons. There's plenty of protons in water, of course, but the fact that this is in this structure at the vortical nature, and yeah, this is it's a big shocker for me, really. And here, what's this one? 45 is on this outside area as well. You got silver there. What? Copper? Sorry. Have I got something wrong here? 44 has got copper. So this center bit has got copper, and 45 has got silver. Okay. All right. Well, there you go. I would imagine, you know, my ring here, okay, I got this from a nugget from Alaska. It's one nugget, and it made both of our rings, my wife and ourselves. And the reason I chose Alaska is because relic neutrino condensates come in, and so they would have aggregated in this gold. And I actually did an SEM on this, and it was basically pure gold with about, I don't know, I can't remember, it's something like 12 or 13% silver. The elements are found together. If we are synthesizing silver here, are we but a few minutes away from synthesizing gold? That's just madness. It's just madness. But, you know, we've got to molybdenum, and look where that is on the periodic table. Molybdenum is here, and silver's all the way over here. Okay, so silver's the heaviest element we've seen potentially synthesized. I don't know, but potentially synthesized. It's a drop down from copper. So you can kind of think about it. There's a school of thought that in alchemy, they would, if you start with copper, you then layer a skin of atoms on the outside, and nucleons on the outside, and you end up with silver. And then you layer a skin of atoms on the outside, and you end up with gold. If we're synthesizing silver, then you're one skin away under that thesis or theory from synthesizing gold. There we go. But we appear to be making molybdenum. We appear to be making silver. That's multiple samples have got silver in these core structures. Not high concentrations. The molybdenum was shocking. That was shocking. But like I say, molybdenum is probably the easiest heavy metal or heavier metal because of this 2 CaO goes to 1 ZRO, 2 CaO. 2 CaO goes to 1 ZrO2, observed by Bolotov, and then you just need to add molybdenum. And also, we saw zirconium synthesized in the work of Echo from Suhasralkar. So zirconium was synthesized in there. And also, if you recall, in the flux loop from Lion. So we had the two poles shooting across the valley. I called it cannon. And in that material, there was zirconium synthesized in there. And again, I believe that is this 2 calcium oxide goes to 1 zirconium O2 synthesis. And so this is not so much more of a jump on from there. So, wow. Yes, Leclerc, I think you've done it. But I think because we are able to focus, and aluminium is a beautiful fuel for this. It's just a beautiful fuel. So you could end up, because you would have resonant nodes, not just only on the surface, you could actually put almost like a heat exchanger grill, you know, like lots and lots of layers, like 15 layers in your ultrasonic container, and just hit it with, like, I don't know, 10 minutes of sound, and you could have really serious measurable amounts of elements that you might want to keep, you know. And you'd be converting kitchen foil into really nice stuff. How crazy is that? It might be completely start raving bonkers, but I'm going to show you something now. I'm going to show you something now, which is my little takeaway for the night. I think we've done. Let me just see if I've missed anything that I want to share with you tonight from this analysis. And it's just been a total pleasure to be able to do this with you, really. Oh yes, I found something that I wanted to show you. This one here, because for me this looks like one of these spiral bullets flying around in the reactor. And when I say reactor, it's just a denture cleaner from your local hardware store. It can't be this easy, can it? It can't be. It was just ridiculous. Oh dear, let's have a look at what this is. It just makes such a joke of mining stuff, doesn't it? It can't be this easy. It just can't be this. It's got to be wrong. It's got to be wrong. Let's all take a reality check and pretend this never happened. Okay. Okay. All right. Unfortunately, David Hudson died in, I think, 1996. Sorry I haven't been very interactive with your comments tonight. I just kind of like... I'm enjoying the analysis here. Such that it is. It's very raw. It's very raw. Okay, so we're looking at samples 16, 17. And in fact, I'm just going to show you the image itself first in all of its glory, because it's very glorious. And then we can look at what it is. Okay, so this is very similar to the structure that I found in the sample from, who was it? Echo from Suhasralkar in India. It's about half the diameter and half the length. So the one in India was 5 microns wide and 10 microns long, and was nearly entirely silver. It was nearly a pure silver structure. In his ultrasonically driven electric discharge nickel sulfate plating in water system. And in this case, this one is about 2.5 to 7 microns at the head, and it's about 5 microns long. Is that right? Maybe, yeah. But what I like about this is the way that this material is blending into the substrate, and it almost looks like it came through the aluminium and it basically got disrupted and got caught by it, and it just kind of ripped off a little bit that it left, and it's like up here. So it's kind of like it blends into the material underneath. So let me just set this up with the EDS data. Okay. Okay. So 16. Okay. Let's see what we have here. If I can I do that and that? Get them all in shot. Let's see. Okay. What do we have? Well, what do we have? Okay. What do we have? I'm loving doing this like real time with you guys. Really. Okay. So what have we got? Okay. 16 is right on this. This is the equivalent of the silver bullet that was in the Echo system. And what do we have? We have 16% aluminium, little carbon, whatever. Oh, hold on, wait, seriously? Oh, look at that. Look at that. We have 33.64% copper. 33.64% copper and 9.3% zinc in this, what I would consider is a frozen coherent matter traveling wave, pending more examples. So it's got aluminium, copper, and zinc. Aluminium, copper, and zinc, and very little in the way of nitrogen. Yeah, that's basically what it is. So have we synthesized copper, zinc, and molybdenum and boron in this? I don't know, but this looks like it's making copper blob, and it's blending into what was an aluminium sheet. You know, this is how I imagine the coherent matter would interact, and you're literally just seeing it. You're seeing it doing it. This blending area here, where it's kind of like it's one thing and another, like whatever this copper and stuff is now blending into the substrate. Okay, so what do we have in spectrum 17? That's where it's kind of blending into what was aluminium, in my view, maybe. Right, okay, so there we go. We've still got the copper. We've still got the zinc. The copper has dropped significantly. Boom! There we go. Oh, that's your money shot. Your copper is dropped by, I would say, it's much less than a third. Your zinc has dropped to 1/10, almost exactly a tenth. There's now calcium in there. Your aluminium has gone from here, or well, the aluminium hasn't changed much, but that is in my view the substrate. Your carbon's all the way up to 33% from. Make sure I'm on atomic percent in both. Oh, this is just beautiful. This is beautiful. What you are looking at here, in my view, this structure here. Absolutely beautiful. This is a coherent matter structure, in my view, that went through the aluminium from the backside, and it got disrupted as it came through the impedance change, and it literally made it through, but the coherence was collapsed. It collapsed the coherent state, and it came down as mostly copper and zinc, and it blends into the aluminium material from whence it came, with the remainder of the carbon left as the alpha condensate. That's just beautiful. That's just beautiful. You know, I'm real time watching this. Real time. You are experiencing just that finding right now. I don't know whether it can be replicated. I expect it will be many, 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 many times over. But you're seeing it real time right now. Real time. That for me is the big win of the night. Yes, we see molybdenum. Yes, we see silver. But what you're seeing is, in my view, this coherent matter traveling wave that's come through, interacted with the aluminium and caused this structure to come out. I'm loving that. I'm really loving that. And you know what you're looking at here, what you're looking at is a very small percentage of a. In fact, look, I'm going to show you where this is, and look. So this structure here, this is this peak with the divot, but it's actually down here. Yeah? So you could imagine a scenario where whatever was going on in here on the underside of this, because it is on the underside that the bubble is occurring, that there was an explosion and part of whatever it was that was coherent shot out through the side of the cone. And that is what you're seeing here. If that's what's happening, it's absolutely astounding. It's astounding. That's the only words I have for it. It's just astounding. You are seeing, because I can tell you, I've seen under the high-speed photography and microscopes these corkscrew spiraling things going through in the experiment, like these things that are physically, you can see them spiraling through the water, just like the glowing ones that we see in the Vega experiments. Is this what we're seeing here? Could it be? Could it be that? And we're starting with water, whatever is in the tap water, and aluminium, and sound, and you're creating copper and zinc. Wow. Wow. Okay. Right, so I've got something to close out here and then a request. I've thoroughly enjoyed this analysis session with you. Like I say, it's super duper raw. I haven't even organized the spreadsheet or whatever. But this just been beautiful. And now I've got a little bit of crazy for you guys. A little bit of crazy. Because I think that's what we need to do. Otherwise, people might take us seriously. So I've got a little bit of crazy. And on that, I'm going to do a little interlude whilst I go and visit the men's room. So I'm going to give you a little video to watch whilst I do that. So, where is it? Ultra crop circles. So this was actually from the actual day on Monday. So hopefully you can hear the audio. So this is a vortex pit with a split in it from an ultra experiment that ran for maybe 90 seconds. And we've got a twisted vortex filament coming out here, and it's got calcium and silicon in it. And here we have another pair. And if we go and look at the split here, we have this structure coming through. And if you look at it, it has, look at the spectra here. We've got 23 is, where's 23? 23 is on the top here. So 22 is over here, and that is basically aluminium and a little bit of carbon and oxygen. And then we go to 23, which is on the top, a little bit of aluminium, carbon and oxygen. And if we look at 24, we can see the silicon coming in, and we can see very little aluminium, it's mostly carbon, and there's some little iron coming in. And if we look at 25 here, we've got aluminium and silicon, quite a lot of silicon, so that's kind of increasing. And if you actually look by weight percent, on that 25, we've got 8.6% by weight is iron, and we've got 13.39% with silicon. 24 is lower, and then the original material has no iron or silicon in it. Okay, back in the room. Thank you for the break. I will pull up my last image here. Bear with me a few seconds. Okay. You ready for this? You ready for a little bit of crazy? Crazy time! So, this is the still frame that I chose for this video, and I encourage you to go and see Ultra Fingerprints. And I was working through these high-speed photography images earlier to explain the bubble and so forth, and showed that it occurs in magnetohydrodynamic structures. And here's a very close-up image showing how the carbon gets deposited, and then I showed this helical beam coming into the center. Then I showed the these figures of eights with the hexagon and the raised bit in the center, and the peak with the dimple in the top, and how this exactly matched what you observed in the Amasa vibrator plate, and how that this has an analog in the magnetoelectrodynamic, or electro, or whatever, you know what I mean. And I showed that there is a vortical structure, and that it goes one way on one side and one way on the other, and how this influences, and how we came to learn about the magnetic structures, and that this had a little S cut in it, and we've seen that in Bin-Juine Huang's. And then all of this was published on April the 8th, 2021. But I was sent just by a random person, or something that I would subscribe to, or someone would subscribe me to, a video on August the 26th, yes, so that is less than 1 month ago today. And in that video, which is about some aliens, I saw a couple of frames, and I was watching it on double speed, and also I was skimming through it because it's quite long, and you can go and have a look at it. The link's in there, and it's been in there since August the 26th. And there were two things in that video about crop circles, and I think they're from the 1980s. There was this one here, and there was this one here. And I thought, holy moly, they look very, very, and this is the video, by the way, UFO aliens, human or extraterrestrial. So you've got two structures here, and you've got links between them, okay? And then this one, well, I'm going to explain what I think it is, right? And so the reason I saw that as being interesting is because this looks like the two circles with the links between them. This is exactly what you're seeing here, okay? This is the affected area where the bubble is spinning around, and you've got the raised bit, and this is the dimple. So I thought on, when was it? On Friday or during the day, that I would see how this structure, whether I was right in thinking it is relevant. And I'm going to show you something, and I think it's a little bit of a mind stretch, but give me a second. I'm going to pull up the PSD. So, where is it? Where is my PSD? So we're going to go back to the beginning, not quite to the beginning, completely to the beginning, but nearly to the beginning. Here we go. This is our first one, which is not fully done. And if you recall, we have a kind of helical thing on this bit that's raised, and it's hexagonal, or at least pentagonal, but I think it's hexagonal in structure. And this is the lowest point. This is a high point in the low point, and this is our pit. And then this is our kind of flat top with a dimple in it. And we know that this does a similar thing to the other side. Okay, so this is our structure. Now, this just so happens to be the very first one that I captured. And it seems to be a bit like this. But what I'm going to do is I'm going to overlay the smaller part of this structure here. And all I've done is I've mirrored it. I could have mirrored my SEM. It doesn't matter. You'll get my point. And this is what it looks like. It is an absolute 100% geometric match. The ratio between the gap in here and the top of the flat top, and the ratio between this and the bottom of the pit, 100%. The loop around this side showing the highlight on this side, and the loop around this side showing the highlight in the pit, is 100% match. Okay? Then I thought, what about this other part of the structure? Well, let's have a look. There you go. So I put the other part of the structure in here. We got the center spot, right? The outer rim is the outer rim of the point at which it goes from flat to start to curve. And this center spot is the center of the center that I showed you. You can see in this bit here. It's the center of the center here. So there's a gap, and then there's this outside bit, okay? Center of the center, the gap, which has got the hexagon bit, and then the outside. What is this donut they've put here? Well, that is the bubble. It's not the clearest image here, but that is the bubble. I believe whether it is white hats in the black world, aliens amongst us, or extraterrestrials, whoever made this crop circle absolutely, certainly knew this technology. without a shadow of a doubt. And were trying to tell us. I can't give any other explanation. They have the bubble. They have the torus. It's exactly the right proportions for the inside of this, as you see here. Absolutely identical. Absolutely one-for-one match to this structure. And what they are, in my view, doing with these two curve sections is they are saying that this is pushing material in. It's cohering, it's forcing and condensing it. It's condensing matter. This is condensed matter technology. I think some good force was trying to tell us we have a technology, it's so easy, and you know, that's the key. That is the key. And it's just so nice that in this one blog published on the April the 8th, that on August the 26th, I was sent this video just out of the blue, and I just you know, my view on some of these things is, if it gets sent to me, there's probably a reason. I don't think of that with everything, by the way. But this doesn't make any sense. It doesn't make any sense about anything. But it's 100% certain that this is a complete match for this. And could it just be that some benevolent, some good force out there, some spirit, be that a alien amongst us, an extraterrestrial, or a good spirit who did work in research maybe in the 50s and 60s and 70s and was about to die or whatever, but maybe they're saying that the coherent matter technology that produces ball lightning, the coherent matter phenomenon that produces ball lightning that we are using to create these crop circles is the same technology that you can create with water. All you need is water and sound. All you need is water and sound. And I've already shared with you that all you need is sound and matter generally. And it will create the same thing in the center of matter. I think it's really that simple. You have the bubble exactly represented here. Bubble, exactly represented. That is the bubble that you see here. You know, I have no other explanation for what I'm seeing here, is that someone wanted us to know this technology. And thank God for who they are. Thank them for doing that. If it's God, then even better. Great. Because this is the God's toolbox. And this is exactly how it's working. There is no scarcity. There is no scarcity in my mind. We can make anything we want to out of the matter that's available. And from that, we can make, you know, no one needs to be starving. Yes, you can use this technology to turn things to dust. Yes, you can. Yes. And yes, you can push it too far and you can make radioactive stuff. Yes, idiots. Idiots. People who can't think very much, like to just damage things for profit. Idiots. Not a shadow of a doubt in my mind, this is coherent matter technology. You are seeing a coherent matter wave beam, in my opinion, coming through this aluminium, and it's already almost all copper and zinc. Stop killing people for profit. Stop it. And stop with this scarcity nonsense. Stop it. Anyone can do this experiment. Anyone can do this experiment. And someone was trying to tell us in the 1980s, someone out there, some good force was trying to help us reach for the stars. Not destroy our planets, not dig massive great holes in the ground to find a little bit of something we need for something. It must be such a joke to these people, or entities, or whatever, God. It must be such a joke to them. You are destroying your planet for a little bit of this and a little bit of that. This is the God's toolbox. And anyone can go out and spend $35 and test it. It either does exist or it doesn't exist. But transmutation happens. People need to come to terms with that. Leclerc was transmuting matter. He was transmuting matter to every element in the periodic table, and he was using water and cavitation, which is driven by the sound. That's it. That's it. That's it. And he's not the first. He's not the first. Huh. I expect the ancients were doing this all of the time. All of the time. What a society have we built? We think we're clever. Nature's given us the answer all along. It's in the streams. Go and see a bit of nature. Go and walk next to a stream and see how vital it is. Why is it vital? Why is everything wanting to be next to moving water? Why? Why is it doing that? It's because of this, in my opinion. This is why it is. This is why a Marsa, if he vibrates his vibrators, he finds every element in his water after a period of time. Why? Because of this. That's the reason. Why did Roger Stringham create all the elements? Why did when he was working with Leclerc, with Tom Claytor published in 2019, why are they taking whatever element it is, doing a bit of sound on it, and you get this structure which they hadn't recognized was this figure of 8, and you're getting all of these different elements synthesized? We are at the dawn of an old age. We are back to the future. We are back to the future. So, with that, I will ask if there's any questions. Sorry for the tirade there, but I'm kind of had about enough of the idiocy going on and the misapplication of this technology. And I would like to see a new vanguard of people that are able to actually deliver. I know what it is, W for truth. I know what it is. And it is that. It is that. More tirades. We live in a universe of abundance with unlimited energy, and we have the power and the understanding to transmute elements to whatever we want into and out of physical reality. That's the reality of what you are looking at right here. And yes, you can teleport. Yes, it will be anti-gravity. I'm sorry those people that don't like that being discussed, but yes, it will be that too. Ball lightning does all of these things, right? Yeah, I've heard about Walter Russell. Yes, I've seen it. And he got quite far. He got quite far, but I'm tired of these people that find something and they want to protect it for themselves, you know, so no one actually really gets to benefit from it. I know he tried to put things out there, but if he really had got it out there or really understood it, we'd all be using it now. We'd all be using it, just like nature always uses it. We're part of nature, but we're trying to impose a really distorted vision of what nature is onto nature, expecting it to try and bend to our will. No, nature will do exactly what it always does, given a parameter space. And in the parameter space of sound and matter, this is what it does every time. I look forward to it, WP for truth. So how do you do it in bulk? Well, you're using 46 kilohertz here, 43 kilohertz. And that produces resonant nodes at a distance, and you can work out the distance by looking at this. This is 100 microns, so you can work out your distance exactly, right? In the medium of aluminium in water. What Roger Stringham did, and you can see it if you go to nansoft.co.nz and look at the Lena events and put in Stringham in there and look at the latest paper by him and Tom Claytor. They moved to what he was always working at the 20 or the 40 kilohertz range because you can see what's going on because of the scales. But they're now working in the 1.6 megahertz, and so you get many more nodes. So you get a vast increase in the amount of transmutation. Well, guess what? If you coat aluminium with PZT and then you hit it with microwaves, so your resonant nodes are the same spacing as the interatomic distance, the whole thing changes. You get it yet? Do you get it? Sound it's so powerful. It's a boson, and a boson which hits resonance, there's no loss in energy, and that's how you're working here. Mighty Mouse Girlfriend, yes, it can help as well as harm. They've already been doing the harm. Not very bright minds have turned this into weapons, and they have used it. They have used it, and they've changed the course of humanity. They have killed millions of people, displaced millions. They've allowed, because they've not allowed this technology to stop us from damaging the planet, they have caused directly the destruction of the biosphere. Directly. And they are using it, I expect right now, because it can be used for this same technology, it can be used for this, to fake global warming. They can use this to fake an alien invasion. Do you understand what we're dealing with? The lies! The insane lies! It's got to stop! It has got to stop! This is our birthright. It is what we are. We're made of it. It is nature. It's got to stop the lies and the killing for profit. We live in a world of abundance and a complete sea of energy that we can, using this technology, we can stop the famine. We can stop the destruction. Just everyone has to know. Everyone has to know. They have to know we've been living a lie for thousands of years. Thousands of years we have been living a lie. We mustn't let them do another round of taking our freedoms away. We mustn't allow another round of that. Once they've done the never-ending virus, they're going to do the never-ending alien threat. And by the way, you can flip the poles with this stuff. There are several ways you can reset the planet. And they've done it before. I'm pretty certain they've done it before, and I would look out for 2032 to 2033. They're going to do it, probably whatever. We can only make this stop if we work together. We do what nature wants us to do. Work together. Not be separate in the supermarket. Not be separate and not go to church. Not be separate and not meet our loved ones. Not be separate and divided. We have to work together. We have to work coherently as one. And we have all the power. All the power. The universe, it's everything. Everything. We have all of the power to get through this. They are dividing us. They are keeping us separate. They're preventing us from talking. They are censoring us. It's an all or nothing approach. This is the scorched earth, and it's not their final trick. I tell you, it's not their final trick. You can do this experiment. Either it is what it is or it isn't. It is so simple, my 5-year-old daughter could do it, including the instruction time, in 20 minutes. If she had a scanning electron microscope and we had a fast dryer, the whole thing would maybe take less than an hour. From getting the stuff, teaching someone, doing the experiment, and putting it under the scanning electron microscope. Done. Done. It either works or it doesn't. But I think there's 30 years at least of experimentation evidence you can go through using the MFMP's linear events database. Thank you, Philip Power, for working on that. And you can go and you can search and you can find the experiments and you can see Roger Stringham in 2012. He's saying that this is coherent matter. He's thinking it's just two deuterons fusing and making helium and it blows it up. No, this is a collective state. He's where Matsumoto was in 1990 in thinking. Matsumoto realized by 2001 this is vast numbers of nucleons, microns wide, that are transmuting simultaneously. What are they doing that for? Because they're all becoming denatured. They're becoming a macro quantum object. That is what they're doing. That is what they're doing. They are not one atom anymore. Guys, you have the ability right now to go and test this experiment, and even if it doesn't work, you got something to clean your dentures with when you're older, or your glasses, or jewelry, or whatever. But I'm pretty sure it's going to work. I'm pretty sure it's going to work, okay? And it's literally, it only takes a certain number of people to do this, and it's a complete watershed moment. A watershed moment. You think about what we're talking about here. We're talking about changing up and down the periodic table. We haven't got enough copper, let's make some copper. We haven't got enough silver, let's make some silver. We haven't got enough boron, let's make some boron. Yeah? Work with what the technology does. Work with what nature is doing. And work with whoever it was. Thank you. Thank you. If you're dead or alive, or you're a spiritual entity, or you are an extraterrestrial, or a, alien amongst us. Thank you, whoever it was, for sharing this. Yeah? Thank you. There is literally no way that this structure is not this. And that the bubble that you see here is not the bubble that they represent here, and the cohering forces that are coming to the center of that bubble. Now, So this is what I need to ask for you. I don't know much about crop circles. You know, my dad, I told you before, he was a super big mason, and he took it. The only crop circles I ever saw in my life, he decided to drove me to specifically see these crop circles. I don't even remember what they were, but they were definitely crop circles, and they were pretty impressive. So I would ask those people that have more experience in crop circles to look at what we've been talking about. You know, I have the Chilbolton crop circle on my ring, right? Yeah, the answer to the way that the communication worked here, right there on the ring there, and that's a custom design for my wedding with my wonderful wife Kim, and that was the moment, you know, it was in 2017. Someone was trying to tell us something, and that is the most significant crop circle until I found this one. And this, for me, this is explicitly telling you how to do coherent matter technology. And this will be the same thing, it'll just be on a different scale. And it will be the same in solids as well as what you're seeing here, which is basically a 2D plane cut through a solid. It'll be the same. It'll be the same. You don't have to guess. This is what it is. And they are telling you exactly how it works. Without a shadow of a doubt in my mind, there's no other way to interpret this, in my view. They knew exactly what they were doing when they made this crop circle. So I would like, if there's people out there that have much more experience than I do, like, you know, I don't have a lot of experience, as I said, in crop circles. If you know a lot about crop circles, start putting a catalogue together. Maybe we'll add another section to, if we can. It's a lot of work, I'm sure. But we catalogue date, time, what the crop circle is. Maybe there's already a database out there. I'm sure there's probably someone that's done this. There's a lot of people that have been interested in them over the years. And I am certain that we are going to find in the genuine crop circles some extremely important hidden gems. Extremely important hidden gems. That will be telling us exactly how this technology works. But I think almost the only one you need to know is this one right here. This is the crop circle. And that was why, in my view, the universe sent me that video that day. Okay, so I'm going to see if you've got any questions in there. If you've got questions, that would be great. It's great to see you having a good conversation. And okay. Colin Andrews has a big archive. That would be great. Maybe if you know Colin Andrews or someone knows him, forward this presentation to him. Kim has been incredibly patient to put up with me doing this research and for the poverty that we've had to live through. But I can honestly say just the live analysis session today and the potential implications. But this crop circle and you know, it's all been worth it. It really has. Definitely for me. There's no next tech after this. This is how you manipulate the fabric of the universe. There's no next tech after this. You'll have a lot of things that look like different technologies, but they'll all be this same thing. It doesn't matter whether you're doing faster than light, time travel, teleportation, you know, dematerialization of matter, dematerialization of matter, cloning exacts, all kinds of things. Yes, this is Christ technology. WP for truth. Yes, it is. Jesus was trying to teach this to people. He definitely spent his 12 years in the, 18 years in the desert. Well. Okay, I think people are telling me that Simeon Hain is good at the crop circles type of thing. So, Simeon, if you can help with this, I don't know whether you're still on the chat, but that would be fantastic. I mean, if you can just throw me candidates, obviously I've seen a lot of structures over the last nigh on 10 years doing Lena. So it was just like when I saw this video, I go, that's important. It's a long video, but it's just a quick shot of this one crop circle and I go, someone did that for a reason. Back to boring. Good for you, Anbeck. Already planning your experiments. Great. As I said, what I'd like to see Alan do is to, like, you know, just do experiment after experiment after experiment, but to do them with increasing amounts of time. You know, also when you do these experiments, you get an area that typically gets eaten away from the aluminium, and then there's areas that are near that which might be a certain level of intensity, and then there might be areas further away, so that there might be another way where you can look at the variation in intensity by looking away from the main resonant node, the distance away from that with these figure-of-8 structures. And by the way, it's an infinity structure, if no one's noticed that. and yes, it's a yin-yang, of course. Lucas, the most important thing in this universe is love, and comes with that respect. WP for truth, yes, we can light the world bigger than Nikola Tesla. Yes, absolutely, 100%. Who are they, though? I don't know, and it almost doesn't matter. Whoever they are, they knew exactly how this technology works. Yes, the event had two resonant structures. Gordon. So I think what we're seeing is that as the cycle progresses, you get more and more iron. I think that will produce the iron crenellated spheres. The iron crenellated spheres are a focal point, and I think they're absolutely critical. But you know, the transmutation is due to this dual vortex structure. Okay, I'm going to see anything down the bottom. Otherwise, I'm going to probably call it a good night. Okay, so essentially, let's start at the beginning. This was ultra crop circles, and we looked at the work, recent work of Professor Bin-Juine Huang at the New Energy Center, Department of Mechanical Engineering, National Taiwan University, Taipei, Taiwan. And we looked at a whole bunch of samples. One sample from one very short experiment. a number of these figure-of-8 structures. And before that, we talked about how it's almost certain that we are generating these FeO2 devices, but we're not using stupid expensive diamond anvils, but we are actually creating them in a range of different technologies, one of which has produced the most clear example, which was in the Vega experiment by Henk. Thank you, Henk. And that the question was the other ball over here the same, and FeO2, and given all the other oxidation states and the low amounts of contaminants other than iron and oxygen, it's very likely that this is FeO2, and that we went back to this one that was sucking the electrons out of the room and maybe creating this atmosphere of electrons, and potentially that is because this is also a FeO2 structure, and everything points to that given the low amount of contamination in here and the fact that it is capturing a couple of these particles in here. And so we can do more work next time on the SEM and nail the fact that this is FeO2, and but I consider at this point that it's pretty much done. Looked at Bin's work, and we looked at that a bit and where the silicon's coming from, and then we looked at his S structure, which shows the circle in the center and the vortex, and this looks like a spiral arm galaxy, and I expect it's exactly the same thing that's working at that level, and a nod to Winston Bostic for suggesting that first. And then I did this quick sketch about how the bubble is forming on both sides of the structures, and how the bubble grows and collapses, I guess, and this leads to the vortices, and that was that. And then the money shot at the end was, well, for me, we saw some potential synthesis of molybdenum, silver, copper, and zinc, and these things could easily be verified by anyone that wants to spend a little bit of their time and a little bit of money, and I do mean a little bit. And there's a long history of transmutation being successful, with possibly the most clear examples being Leclerc, and before him Roger Stringham. But Leclerc was creating every element in the periodic table, and so there's that. And I believe that this is a coherent matter traveling wave, and that this was in a coherent matter state that was mostly copper and zinc, and it came through the aluminium and left this semi-fused in structure. And that at the end we looked at a crop circle that I'd found in a video on August the 26th this year, this one here and this one, which essentially I believe is showing the vortices going between the 2 points that I'm showing on, let's get it here, no, I'm showing it somewhere here, which I had in my title slide from the 8th of April. These structures going between there and there, and so those two crop circles together, but principally this crop circle is showing the bubble in the pit and the cohering forces that it makes, and that there is two structures, and one is a peak and one is a trough, and that is, I believe, a absolute 100% match for what we see here, right the way down to the fact that the bubble is there and that it has the cohering structure with the bubble, and everything lines up exactly. And so there we go. So thank you very, very much for your time, those that managed to stick with us as we got to the punchline here. I think we're at the dawn of an old age. And, it's a special time to be alive if the people that are subjugating us and taking away our freedoms could just get out of the way and let us be able to do what we can do. We need the world to understand this technology, and I think the ULTRA experiment is the best way to do that. Because it is so unimaginably simple, I didn't find it for you, but someone sent me after some of my Ultra videos earlier these old bowls. They're like a big bowl, and they have two like things either side. And maybe I'll dig that video out and add it onto the blog for this. It might have been David Butlier. So David, if you did send it to me, can you send it to me again, the link? I should probably find it. In fact, I'm going to have a look in a sec. And basically there were two things either side, and they rubbed the side, and it produced coherent sort of standing waves in the bowl, such that you saw these things jumping up and down. And it may be that simple, and I believe that these bowls would have been used to make high energetic state and rich in micronutrient or micro minerals, water, and maybe even to sanitize water as well, because Amaza says his vibrator plates is used to clean water. So it might be a very, very quick way to make potable water out of normally unpotable water by using these energy structures to sterilize the water. So if that is the case, then that in itself is a very simple tech that could absolutely transform large parts of the planet. So thank you very much. I am going to say buenas noches, do svidania, dobro noc, buenas sera, bonne nuit, and we need to work coherently, we need to work together, and we need to work as one, and don't let them get you down. Thank you.